on equidistribution, arguments on equidistribution by Jon Chaika.
Thank you very much. So let's just sort of remember the setting. We're on the very nice torus, r squared mod z squared, the real is mod out by the integers. We're considering the map 2, 1, 1, 1, a hyperbolic automorphism of this space. It's got one expanded eigendirection, which is 1 plus the square root of 5 over 2, 1. And the relevant eigenvalue is 3 plus the square root of 5 over 2. And then it's got a contracted direction, 1 and minus 1 minus the square root of 5 over 2. And that has a contracted eigenvalue, which is 1 over this, which is also goes by the name of 3 minus the square root of 5 over 2. And we're considering a family, and as was the case last lecture, we'll only consider one of them for a particular choice of vector. But how does this act on the torus? Well, I act by just adding t times the first coordinate of my vector in the first coordinate, and t times the second coordinate of my vector in the second coordinate, where you can alternately think of this as being calculated modulo 1, so you subtract the integer part from both, or you can think of this plus as representing the addition in the group. All right, and so what's the main theorem of today? It's essentially the same theorem as yesterday, so if v, my v is going to be different, but the argument from yesterday would have worked just as well for that by reversing sort of k, making k is negative rather than positive for this map here, which by the way I'll denote as being a. So this time I'm considering the contracted eigendirection. And this is just because that's sort of the nice way to present it. Then f to the t of v has a unique invariant measure. And we know that the area is invariant, so that measure better be the area. Okay. So let's begin with reduction. So we have the following lemma. It suffices to show for all g, 1 Lipschitz. So that means the Lipschitz constant is 1. Remember, this is just for sort of convenience in our argument. And for all P and Q in my torus, the Birkhoff averages are the same. The integral from 0 to t of g of f to the s. I'm going to drop my v's just for convenience. So I don't want to be writing v all the time, so I'm just dropping that. F to the s of p minus the integral from 0 to t of g of s to the s of q goes to 0. We proved this last time. Let's just briefly recall. If you had more than one invariant measure, you could, because the ergodic measures are the extremal points of the invariant measures. If you have more than one invariant probability measure, and all my measures are Borel, then you have more than one ergodic measure. Now, if you have more than one ergodic measure, that measure has a point that equidistributes for g according to that ergodic measure for each of them. So you get these different, you get that these integrals were different. One of them were converged for the integral of g with respect to one ergodic measure, and the other would converge to the integral of g with respect to the other ergodic measure. Is everybody happy about this? Let me just mention in the notes, I have a different proof of this also. there's sort of a billion different ways to prove this fact, but, so the notes present a different one. All right, it sort of uses Fubini. Okay, so this is our goal theorem, and so as before, we'll do this by sort of comparing these things, and in place of what we did last time, which was sort of considering what the limits could be, and using equicontinuity, we're going to use a sort of a more direct procedure, which I'll call orbit matching. Okay, if you want to sort of think of that in your mind. So the starting point of this is that we can sort of match points. So we have the following lemma. So if P and Q are in my torus and are arbitrary, please, if at any point I'm writing too small, let me know. If these are here arbitrary, then there exists numbers A and B between 0 and 1 and 2. So that Q is equal to P plus A times 1 plus the square root of 5 over 2, 1 plus B times 1 minus 1 minus the square root of 5 over 2. Okay. So briefly, you can find this by linear algebra. You consider a matrix that has one column this and one column that. You represent the difference vector between P and Q in R2 in coordinates. You apply the inverse of the matrix I just described to that coordinate. And then you use the fact that everything is mod 1 to pick these to be between 0 and 2. Everybody okay with that? Now, of course, absolutely nothing is important about 2. It's just that you want a constant C here. And that's the same thing as saying that my space R squared mod Z squared, which I can think of as looking like this, has finite diameter in the L1 norm I discussed last time, which just comes from these coordinates. Everybody happy about this? Okay, so now we're going to do the key step in the proof, which is the following corollary. If P and Q are in the torus as before, and K is in the natural numbers, and is, let's say K is in the Z. I'll care about the case where it's a natural number, but this all works wonderfully well. There exists 0 less than or equal to A, comma, B less than or equal to 2, so that, let's change this expression, Q will be equal to P plus A times 1 plus the square root of 5 over 2, 1 plus B times minus 1 minus 1 minus the square root of 5 over 2. Okay, and what's going to fill in the blank? Here I'm going to have 3 plus the square root of 5 over 2 to the minus k. And here I'm going to have 3 plus the square root of 5 over 2. Oh, minus the square root of 5 over 2 to the minus k. All right. So I have the same exact expression, but I have these eigenvalues raised to the same k showing up here. And let's just make the remark that I'm going to care about the case where k is positive. So this will be a tiny number, and this will be a big number. Everybody happy about this? I haven't proven this corollary yet. I will prove this corollary in a moment. It's sort of the key idea of the proof, but does the statement make sense that I can sort of insert factors in front of these that sort of compensate for each other?
Sorry, so Okay, so what are the quantifiers for every k?
So I fix my P, my Q, and my K. Those are fixed. And then there's an A and a B that depend on this. And you're probably right that maybe I should have chosen these to be called A prime and B prime. And they should, yeah. Everybody happy about this? Okay. All right, so how did the proof go? Okay, so let X be equal to A to the K of P, and Y be equal to A to the K of Q. Let me say how the proof is going to go first, and then I'll do out the detail because I think it's helpful to see it, but let's just say how it's going to go. I'm going to now apply the lemma to X and Y to get these coefficients, to get this pair A and B. I'm going to pull everything back by A to the minus K to get that this becomes my Q, this becomes my Q, this becomes my P, and I insert these factors by how A to the K acts on these matrices. That's all that's going to happen. All right, so let's now prove this. Okay, so now by the previous lemma, y is equal to x plus a times 1 plus the square root of 5 over 2, 1 plus b times 1 minus 1 minus the square root of 5 over 2. Okay. Everybody happy about that? Okay. And so Q, which is equal to A to the minus K of Y, is equal to A to the minus K of this big expression, X plus A times 1 plus the square root of 5 over 2, 1 plus B times 1 minus the square root of 5 over 2. And now I can distribute my A to the minus K across just by linearity. And this is going to be, my A to the minus K X is going to give me P. A to the minus K, A to the K, P is just going to be P. Plus A times how A to the minus K acts on this matrix. And it's an eigenvalue, so it's just eigenvector, so you just act by the eigenvalue to the power. And then the same exact thing in the next coordinate. Okay, so everybody happy about this? Sort of nothing has happened. Let's draw a picture of what's going on, because I think it's very helpful to draw a picture. I've got my points P, and I've got my point Q, but I don't match them up here. I first multiply through by A to the K. And these points now are some other places in my space, so maybe this is now A to the K Q, and this will maybe be A to the K P. Okay, and I connect them up by two segments in my two directions. I hope I have two colors that work, because I think it's going to be helpful to look at that. Everybody okay with this picture? And then I pull them back. I just pull this whole picture back, and the picture I have is going to be, okay, this is expanded a lot. So it wraps around in some complicated fashion. Comes extremely close. That's the picture. Everybody happy about that? Great. Okay. So now I think I'm prepared to prove the theorem. So proof. Maybe I'll do a proposition first. For every P and Q, in my torus, r squared minus z squared, and k in the integers, there exists, maybe I'll do k in the natural numbers, there exists s less than or equal to 2 times 3 plus the square root of 5 over 2 to the k, which by the way is just going to be 3 minus the square root of 5 over 2 to the minus k. I forgot the 2. There's my 2. So it's this number here. I'm keeping track of this number, and the b is at most 2. So that's where that number comes from. So that for every t, in the real numbers, the distance from f to the s of p to q, s plus t of q, to f to the t q is less than 2 times 3 plus the square root of 5 over 2 to the minus k times the norm of my vector. 1 plus the square root of 5 over 2. 1 close 1. Everyone happy about this? Okay. All right. Now, of course, this is going to give us a similar statement about the difference of their values for one Lipschitz functions. Okay, so now the first claim is that it suffices to show there exists such an S. So that the distance of f to the s of p, comma q, is less than 2 times 3 plus the square root of 5 over 2 to the minus k times my norm. And what's the reason for this? This is because f to the t is an isometry. An isometry. So the distance from f to the s plus t of p, comma q, is on the nose equal to the distance of f to the s of p. Okay, just doing rigid motion of my space. So distances are preserved by these rigid motions, so it suffices to get close once. Thank you. Thank you. Any other questions or typos? Great. And now this comes just from coordinates immediately, okay? By the previous corollary, Q is equal to P plus A times 3 plus the square root of 5 over 2 to the minus K plus B times 3 minus the square root of 5 over 2 to the minus K times 1 plus the square root of 5 over 2, 1 plus B times 3 minus the square root of 5 over 2 to the minus K times 1 minus 1 minus the square root of 5 over 2. Okay? And so F to the B times 3 minus the square root of 5 over 2 to the minus K times P plus A times 3 plus the square root of 5 over 2 to the minus K times 1 plus the square root of 5 over 2, 1 is equal to Q. So let's just say what I've done. I look at what my object does, and I'm just adding t times this vector to v by my motion of t. And so I pick this number to exactly be adding this modulo r2 mod z2 to my point P. And so I've subsumed these two terms into this term. And then this term is just the same as it was before. Everyone happy about that? Okay. Going back to my picture here, I've generated this picture here. And what have I done? I just realized that this is the direction of my flow. This is the direction of Ft. So I flow until I got really, really close, and I just stop flowing there, and I say I'm really, really close. Everybody happy about this? Great. Okay. So now we have the following corollary. For any one Lipschitz function, one Lipschitz function G. Any one Lipschitz function G. For any P, comma Q in my torus. For any K in the natural numbers. For any t in the reals, there exists there exists S less than 3 plus the square root of 5 over 2 to the k times 2, so that g of f to the t plus s of p minus g of f to the t of q is small. It's less than or equal to 2 times 3 plus the square root of 5 over 2 to the minus k times the norm of my vector. So that's going to be 1 plus the square root of 5. 2. Just Euclidean norm. Okay, all I've done is I've taken my distance estimate and I've used that to get a Lipschitz estimate, an estimate for my Lipschitz function, which has linked me back to my sufficient condition here. Everyone happy about this? Great. So now we're almost done. So I'm going to now do the proof, and I'm going to consider this difference of the integrals very much how I did last lecture. So there'll be a piece on which I can match these orbits together, and I'll match them by this shift of this S that I've chosen here. Okay? Then I'll have a leftover chunk of size S on both sides, and I'll estimate that trivially by twice the diameter of my space, or by the diameter of my space. Oh no, I guess it's by the diameter of my space. And then I'll be pretty much done. Okay, everybody happy about that? All right, so proof of theorem. Okay, I'm about to do it, so if the question, okay, but yes.
So P and Q are fixed, then S is fixed. So S over T is going to 0, okay.
Yeah, great. Yeah, it might be helpful to change this to be a T.
So John, I have a stupid question.
Mm-hmm.
Why the proof today is so easy with comparison to the proof which you gave yesterday? So, okay, so yesterday you dealt with an unstable Hora cycle, today with stable. And why?
There's really no difference. I mean, it's just, I could have reversed directions and taken k negatives. There's really sort of nothing different going on. I think.
So is it the same proof?
No, it's a different proof. I think it's really a different proof. I'm going to basically prove the same fact in 3 different ways. Today is day 2, and tomorrow I'll use mixing to do it, mixing in flow boxes too.
Okay.
So last time was sort of a topological argument. This one I'd call orbit matching, which is really about boundedness of diameters. I hope this will be clearer, especially as a consequence of my second lecture. And tomorrow's I'll deal with tomorrow. Did that answer your question?
Yes.
Okay, great.
Okay, so it means that this is a didactical tool to learn us something.
Yeah,
deeper.
so I think there can never be enough of me saying this fact. What I'm doing in my lectures is somewhat absurd. I'm giving harder proofs of very easy theorems that probably have 4 or 5 proofs that are easier than the one I'm giving. I really am. I'm giving bad proofs of the results I'm claiming, but the point is they generalize to give very good proofs in harder settings. Okay, so I feel it's always great to say that, so thank you for the excuse to say that. Okay, so proof of theorem. Let P and Q be given. Let P, comma Q be given. And K be given. Be given. And maybe just to be completely clear, I don't want to sort of be observed, so let's assume that. So the relevant situation that we should have is that 3 plus the square root of 5 over 2 to the k is much, much smaller than t. Okay, that's the relevant situation we're caring about. That's where our estimates are going to be good. Okay, so now what I want to do is I want to estimate this picture. Let's move forward. Yeah, I think I should leave up that. Yeah, maybe I'll erase. Yeah, I'll start doing the proof and I'll move over to there in a minute. So now what I want to do is I want to estimate the integral from 0 to t of g of f to the t of p minus the integral from 0 to t of g of f to the t of q. And let S be given as in the corollary. Let S be as in the corollary. So now what I want to do is I want to put this here. Okay. So what do I have? I have that this integral is equal to the integral from 0 to t minus s of g of f to the t, no, sorry, s to 1, s to t, of g to the ft of p minus g of f so I will do 0 to t minus s of f to the t plus s of p, f to the t of q. Okay, I've got this term. And then I've got two smaller terms. I've got the integral, I should put absolute values over everything, the integral from 1 minus s to 1 of g of f of t sorry, this now is the integral from 0 to s of g of f to the t of p minus the integral from 1 minus s to 1 of g of f to the t of q. So I should have been looking at my notes, but I think I've done this right. Okay, so I start at 0 to t minus, I'm going from 0 to t minus s. These 2 points are going to be close together. That's just the whole point of my corollary, that this is going to be well controlled. And I'll have my matching so long as I'm so I'll have my matching so long as my time parameters match up. But once this t is equal to capital T minus s, this will become bigger than t, and I'll no longer be in the region where my segment is defined. Everybody okay with that? All right. And then there's the pieces of the integral I haven't considered here, and I think I've done everything correctly. Everybody happy? Okay. So now this term is very, very small. So this term is less than or equal to t times, let's say 4 times 3 plus the square root of 5 over 2 to the minus k. Okay. And this term is less than or equal to 3 plus the square root of 5 over 2 to the k times the diameter. Okay, and I need a factor of 2. Oh no, I think that's correct. Okay, everybody, so let's talk about where these estimates come from. So my interval has a length of t minus s, so that's clearly smaller than t. Okay. I have that for each point, these are at least this close, but that's not right. I have another factor of 2 I have to take care of, and I have my norm to take care of, so I just group those together to give me this 4. Everyone okay with that? And that just comes from the Lipschitz estimate. And now the most my one Lipschitz function can differ at any 2 points is the diameter of the space, and so I'm integrating over the length of s. But if you remembered, I had the following bound on the length of s. I have an upper bound on how big s can be, and I just plugged that in here, and I was correct. I left out a factor of 2, sorry about that. And so that just comes from this estimate here. Who's with me at this point? Okay, Everybody's happy? Okay, and so this, as k goes to infinity and t goes to infinity faster, this goes to 0. Okay. Any questions on that endgame? Okay, so that's a very nice argument, and I like this argument for two reasons, because it generalizes in sort of two ways. Maybe I'll do that over here. Does anyone have any questions on the argument at this stage?
You said you have a unique ergodic measure. Do you have any description? How to describe this measure?
Oh yeah, thank you very much. This is a great thing. So in this nice situation, we know one invariant measure already. It's the measure coming from the area, Lebesgue measure. Because these are translations, and Lebesgue measure is invariant under translations. We know what one of the invariant measures are. We know there's only one, so they have to be the same. It's the measure coming from the area. Did that answer your question?
Yeah.
Thanks for the question. Great question. Okay. So this argument generalizes in two ways. Okay, A. We don't need our map to map the torus to itself. We don't need A to the K to send our torus to itself. Just to a torus of bounded diameter. And this will be my lecture this afternoon.
Uniformly in K.
No, on a subsequence of Ks. Okay, but I'll address this in more detail next lecture. And then B, we don't need to match the whole segment, just a definite proportion. We don't need to match the whole segment. Just a definite proportion.
But you use also an assumption that you deal with eigenvectors.
Yeah, so we still need directions of expansion and contraction. I just want to highlight two different settings in which it can generalize. And we'll still be dealing with directions of maximal expansion and all the expanded directions and all the contracted directions. Okay. I'm going to take as much time as I have to explain as much as I can about B. Okay? And in order to sort of make this not completely disconnected from reality, I want to explain a different situation where this works. So what I want to do is I want to consider a different space. Okay? So I drew a picture of my torus before, and the opposite sides are identified. I want to build a new object, a genus 2 object, where opposite sides are identified. So I want to identify this side by translation to this side. I want to identify this side by translation to this side. I want to identify this side by translation to this side. And I want to identify this side by translation to that side. Okay. So if I'm looking at a neighborhood of a point here, what does the neighborhood look like? It looks like this. Because this point here is the same as this side. There's identified by parallel translation. Everybody happy about this? So this is an example of what's called a translation surface. And what I can do is I can have a flow in every direction on this object. Okay, so it emits a translation flow in every direction. In each direction. And why is this? This is because if I hit everything makes perfect sense what it means to flow in a given direction while I'm inside of here. Directions make perfectly good sense. But when I go and hit the side, I'm identified via translation. And translations preserve angles. So the angles to a fixed direction, say the horizontal, is preserved the entire time. So no matter where I am in the space, I can say, start flowing at angle theta from the horizontal, and that will globally make sense all my way around. Everyone happy about this? So now I want to consider a very special translation surface, where this parameter here is the golden ratio, 1 plus the square root of 5 over 2. This side here, this inside box, is a 1 by 1 box. Okay. And what does that mean? That means that this is 1 plus the, this side is also 1 plus the square root of 5 over 2. Okay? And so what that means is that means this piece here is 1 plus the square root of 5 over 2 minus 1. So that's going to be 1 over the golden ratio. And that's also going to be square root of 5 minus 1 over 2. That's going to be the length of these two sides. Everybody happy about this? Okay, so now if I've set this up correctly, what you can see is you can see that 1 plus the square root of 5 over 2. So let's give this guy a name, let's call it x sub L. Looks kind of like an L. This, by the way, has a name, it's called the golden L. It's very sort of important in this topic. It's kind of one of people's favorite surfaces.
The golden what?
The golden L. And that's because these numbers are the golden ratio and it looks like an L. It's very suggestively named. And then this sends the golden L to itself. Okay. And how can I see that? So I can see that by thinking that I've got two cylinders here. I've got a cylinder here. On one side it's 1, and the other side it's 1 plus the square root of 5 over 2. And what have I done? I've sheared it. And so what I can do is I can cut here, and I can glue it back together, and I get back the cylinder itself. I have a map of the set of the cylinder to itself that doesn't fix points in this lower cylinder, but it does nonetheless send the cylinder as a set to itself. And then similarly for the upper cylinder, we have a side length of 1, and we have 2 over the square root of 5 plus 1, which, by the way, is also equal to the square root of 5 minus 1 over 2. Okay, Gesundheit. So its reciprocal is just given in this way. We've got this nice numerology, and so this same exact map sends it to itself as well. Everyone happy about this? Anyone happy about this? Let's see, who's happy? Okay, great. We've got some happiness.
I was actually, because I wanted to ask, because you know people then also count the angle around the...
Let's not do that for this lecture. right? We're just trying to address one ergodic theoretic argument.
Yeah, I understand, but when you try to imagine this as a surface, and you know there is this problematic point, how should you think about it rigorously?
You know, I think you can actually think about it in the following way. You identify these two sides together. You identify these two sides together. And what you're going to start seeing is you're going to see things are sort of pinching up on each other. So my wife's actually sewn this surface out of fabric, and you can actually see where the singular point is.
And so it's not a surface in the sense that at every point there is a good.
No, there's a great chart there. It's z goes to z squared dz. It's a perfectly nice chart. Yeah. Okay. So I also want to say that in another direction, for the same exact reason, 1 plus the square root of 5 over 2, 1 also sends the golden L to itself. Okay? And that's just by turning our head on its side and repeating the argument. I have a cylinder that looked like this cylinder, but it goes this way. Now I'm just shearing in the other direction. And then similarly, I have a cylinder that looked like this cylinder, but just going in the other way. Everyone happy about that? Now, if I have two maps that fix a space, their composition fixes the space. So now what I can do is I can look at 1 plus the square root of 5 over 2, 0, 1, times 1, 0, 1 plus the square root of 5 over 2, 1. I surely need to check my notes to get this right. If I did my arithmetic correctly, this is going to be given by 1 plus 6 plus 2 times the square root of 5 over 4, 1 plus the square root of 5 over 2, 1 plus the square root of 5 over 2, and 1. By the way, this is 1 plus 3 plus the square root of 5 over 2. But in any case, this is a map, and it's a map of the golden L to itself. Okay, and it has one expanded and one contracted direction. Okay, one expanded. Yeah. And one contracted direction. Direction there. Okay. And we have a similar theorem to before. This theorem is also true for the golden L. Okay. So Ft of V, where it's the contracted direction, has a unique invariant probability measure. And the proof largely goes the same way it went beforehand. But there's an issue that shows up. So as in the situation beforehand, once I got close, I stayed close for all time. Okay. Now, Jonathan said something very helpful, which was the fact that there's these funny cone points. He was drawing our attention to the fact that there are funny points. And when orbits get close, they don't need to stay close anymore. So you can imagine I'm flowing on this side here, and on this side here. Life is good. They're very, very close together. Life is great. But then I hit an identification. I come out here, and I come out here, and they're no longer close anymore. Okay?
Divorce.
What?
Divorce.
Okay. I won't choose those words. They get ripped apart, maybe separated by life circumstances or something. So we can't do the great corollary we had before, where we're matching these points. But what we can do is we can match definite segments of the points. Okay? So what we can do is we can prove the following thing. This is good. There exists a uniform sigma greater than 0, so that for all large enough t, and P and Q in my golden L, so that there exists an A and a B between 0 and 1. Now let's say 0 and 1 minus sigma, so that the distance from F to the T of V plus A capital T of P and F to the T plus B T of Q is less than epsilon for all for all T in the interval from 0 to sigma of T. So I can't match the entire orbit, I can just map to definite proportions of the orbits, and I don't know where they start and where they end. Everybody okay with this? And the picture is very much the same as the picture before. You pick your P and Q in general position with respect to each other. You move them forward, and you get some X and some Y here. Okay? You flow long enough so they both have a segment in the square where you can match them together, and you just match the part that's in this chunk together. And in bounded time, you can match the chunk. So you go forward to match them, you do that at one finite scale, say of length 10, you match a definite proportion sigma, say of length, 1/10 on this point, and you just pull that back to your original picture. Does that make some sense, at least on the level of following it briefly? Okay. All right, so if you look at my
Can I ask?
yeah.
Okay, so at the beginning you could deal with 2 points which are in this very nearby divorce situation. Okay, so what you are doing there? So you cross this singularity and then you start to deal with them.
Yeah, you wait until they flow back into the big box. Okay, that happens in bounded time. You can just kind of look at it. It happens in bounded time. And then the point that's in the box, you can match the orbits nicely.
I see. So you don't care what can happen at the beginning? You wait for good times?
Yep, and then you just match. And you match here, and you match in bounded size, say size at most 10 or something, and then you choose your number of iterates based on how big T is.
Okay.
Did that make sense? Okay, so I want to get to one key result, which is what this all runs on. So this proof we did here, this estimate, it's an absolute disaster. It doesn't work at all. Because this chunk on which I can match is only of size sigma. It's only of proportion sigma. And there's a piece of 1 minus sigma, which I estimate trivially by the diameter. So this is not what we do. This is not what we do. So what we prove is so what you do is the following. It's the following, it's just a fact about Cesaro convergence. Okay, so if the limit as t goes to infinity of the integral from 0 to t, 1 over t of c sub s ds exists, then for any a, in 0 to 1, and b, a comma b, yeah, a in 0 to 1, and sigma greater than 0, the limit as t goes to infinity of 1 over sigma t of the integral from a to a plus sigma t. Let's say, and is L less than infinity. A plus sigma of C sub S minus L is equal to 0. And moreover, this is uniform. So I can take the limit as t goes to infinity here, and I can take the supremum of a in 0, 1. Because I had no control, so my a's and b's here, they depend on my t. A and b depends on t, so I really need this sort of uniformity going on here. And once I have this uniformity, I can remove that. So this just depends on sigma.
Sigma is less than 1?
Sigma is greater than 1. Okay, so let me just say a word about how this proof goes. So it sort of splits into two cases. One where the A is of definite proportion to t. If the A is a definite proportion to t, I know that the integral from 0 to a of c of SDS is eventually close to L. The average of it is close to L, and then this n time is also close to L. You take the difference of those two. Okay, and you get that on the chunk left, the average is close to L. So you have a bigger chunk, which is the entire n time from 0. That's on average close to L. And you've got your initial chunk, which is close to L. So the segment that's left over has to be close to L on average too. Okay? And then the case where this is going to 0, well, that just follows formally from this immediately. It's easier. Okay, so at this stage, in the last 1 minute of my talk, how does the argument run? The argument runs as follows. You prove the following thing, that if the limit of the integral of g of f to the t of p 1 over t, and the limit of 1 over t of the integral of g of f to the t of q exist, they have to be the same numbers. So you only compare points where the limit exists, because then you know that the behavior of the integral over a definite segment of the orbit behaves like the limiting. And you can match on these definite segments. And how does the end game go? Well, assume you had more than one invariant measure, then you needed to have more than one ergodic measure. And you just use you pick a typical point for one measure, a typical point for the other measure, and these have to be different. So that's the contradiction. Okay, so it uses an extra step. Okay, thank you.
Any questions? I have one. The sigma is, well, in this case, I guess only depends on the XL.
Yeah, it just sort of depends on whatever.
But in generalization, maybe it depends on the genes or something.
Okay, let's not go that way. The way, so, okay, so Juan's question is very well-minded. There's a setting I'm trying to hint at here in a simple situation. There's actually a space of these surfaces. And there's a criterion for unique ergodicity on those that very much runs along this argument. There's another subtlety where sort of you don't match up definite pieces immediately, you sort of go through intermediate stages. And then the criterion is just, you want to return to places where you can match up definite proportions of the orbits. So there you have to make sure you're not leaving compact sets. So usually the quantifiers are, you assume that your guy returns to a fixed compact set, and then sigma depends on whatever that compact set is. Okay? And the reason why that exists on this compact set is you assume it doesn't, and then you pass to a limit, and that wouldn't be a surface. Did that answer your question?
The compact set of the surface.
No, of the space of translation surfaces. Thank you. Yeah. Did I answer your question? Okay, cool. All right, well, maybe I'll just remark. If you're interested in this latter point, I've attached an argument of Chung and Eskin. So this is called Masur's criterion for unique ergodicity. And they have a proof of this in the first 4 sections of what I've attached to the document, which very much follows this orbit matching approach. Yeah.
Okay. What is Masur's criterion specifically?
Okay, so there's a space of translation surfaces. There's a flow on this space called the geodesic flow that's given by the matrix e to the t, 0, 0, e to the minus t. So let's notice that this contracts the vertical direction and expands the horizontal direction. And the statement is if there's a compact set that under this flow your surface returns to for arbitrarily large t, then the flow in the vertical direction is uniquely ergodic. Okay? So, yeah.
Any more questions? If not, we thank the speaker again.